Hi everyone! In this video we're going to start looking at our carboxylic acid derivatives. So let's draw a generic carboxylic acid. And let's also draw a derivative of our carboxylic acid. So this is going to look very similar, except instead of that OH group, we're going to see an electron withdrawing group attached. So this will be our derivative. Now, one thing to note with derivatives is that central carbon on the carbonyl group, its oxidation number stays the same. So the oxidation number of that carbon I highlighted is +3 in the carboxylic acid, and it will also be +3 in the derivative. All right, so let's look at some of these derivatives. So again, these will have electron withdrawing groups in place of our OH group. So we can have, for instance, a halogen, and this molecule would be called an acid halide. Now this halogen is typically going to be chlorine or bromine. We can also replace that OH group with another carbonyl group. And this molecule would be called an anhydride. We could also replace OH with OR to create an ester. We saw that last time. Or we could create an amide. And that amide could be a primary, secondary, or tertiary amide. So those hydrogens on the nitrogen could be replaced with alkyl groups. And then finally we have a derivative that looks a little bit different. This would be a nitrile molecule where we have that cyanide group there, CN. So even though this does look different from our other derivatives, the oxidation number of that central carbon is still +3, so this still counts as a derivative. All right, now the other thing to note is that these groups here on our acid halide and our anhydride are good leaving groups. But notice that on the anhydride, our leaving group does have some resonance between those two oxygen atoms. So that's going to create a more stable leaving group. But that's also going to affect the reactivity of all of our derivatives. So even if we look at our other groups down here, the reactivity is going to decrease with our groups here. So the reactivity of the acid halide is greater than the anhydride, which is greater than the ester, the amide, then the nitrile. But we'll talk about reactivity in the next lecture. In this lecture, I want to focus on nomenclature for all of these different derivatives. So let's start with acid halides. So last time we discussed naming carboxylic acids. So we said that this molecule is called hexanoic acid. And if we turn that into an acid halide, so let's say we have a chlorine on the end there, now we're going to replace the ic acid part with YL space chloride. So let's just highlight that difference. So we're going to turn ic acid into ill chloride. So now this acid halide is called hexanoyl chloride. All right, so let's see if you can figure out this next name. So this carboxylic acid is called acetic acid. And remember to make flashcards for those common names for carboxylic acids, because it will help you to name these derivatives as well. So let's turn acetic acid into an acid halide. And I want you to pause the video and try to name that acid halide. Okay, so remember, we just have to replace the ic acid part of the carboxylic acid name with YL chloride. So our acid halide here would be called acetyl chloride. All right, not too bad. So let's go on to anhydrides. So again, let's say we're starting with acetic acid, and we convert that into an anhydride. So we would need 2 of these acetic acid molecules to make this anhydride product. But what we're going to do to name this product is replace acid with anhydride. So this would be acetic anhydride. So again, not too bad, although this anhydride here is symmetrical. What if we had an asymmetrical product? So for instance, we can combine 2 different carboxylic acids to make an anhydride product. We could combine benzoic acid and acetic acid. All right, so then we have to figure out, okay, how would we name the resulting product? So this would be our product here. Well, this is pretty similar to how we would name an ether. So we would name both sides of the molecule surrounding that central oxygen there, and then we would just end it with anhydride in this case. So it looks like we have benzoic and acetic as the 2 different sides of our molecule. So again, as usual, we want to alphabetize. So we're going to start with acetic, followed by benzoic, and then instead of acid, we're going to use the word anhydride. So this molecule is acetic benzoic anhydride. Okay, let's move on to esters, which are a little more complicated in terms of naming. So let's start with this ester here. So the way that we name esters is we first try to find we try to find the component of our product that was the carboxylic acid we started with. Because remember, we're creating this ester from a carboxylic acid. So in this molecule, this section that I just circled in orange would be our original carboxylic acid. We're just missing the hydrogen. And then we also want to take into account this group that replaced the hydrogen on our carboxylic acid. So it looks like we have a 2-carbon group there, so that would be ethyl. Okay, and then we want to figure out what was our original carboxylic acid. Well, if we kind of go backwards here and just add an H onto that O there, it looks like we started with acetic acid. And we'll talk about these reactions later on as well. Okay, so now putting this all together, we're going to start by naming that substituent ethyl on the oxygen. And then we're going to use the acetic acid name, but we're going to replace ic acid with ATE. So this becomes acetate. And acetate is the name of the conjugate base. So if we remove the proton from acetic acid, we get acetate. So that's the conjugate base. So this is a little more complicated than our previous naming schemes. But in general, what you'll do is start with the group on the oxygen that we circled in green. Then you'll also add the carboxylic acid name. But you're going to end it in ATE instead of ic acid. So that's kind of the general formula for these esters here. So let's do a more challenging problem here. Let's say that we have our ester on a benzene ring. And let's say in the meta position we have a nitro group. Okay, so again, we want to try to find the component of our product that was originally a carboxylic acid. So on this molecule, it looks like we originally had an H next to this oxygen here. That would have been a carboxylic acid, and we're going to include everything that's attached to that group. Then we also want to find the group that's bonded to that oxygen that was originally an OH group. So that would be this methyl group here. All right. So the methyl group's easy, that's just methyl. But what about the orange component? How would we name that? So let's draw what we would have originally had. When we had our carboxylic acid. Okay, so that looks like let's see, what would our parent be there? So the parent group would be this benzoic acid, right? And then we have our nitro group, which is in the meta position. So that would be M-nitrobenzoic acid. Okay, so now we have to piece all of that together. So again, we start with the substituent or the group on oxygen, which is methyl. And then we use our carboxylic acid name. So M-nitrobenzoic acid, except we're going to replace the ic acid with ATE. So methyl M-nitrobenzoate. So that's a lot of work to figure out that name. So again, esters are probably the most complicated derivatives to name out of the derivatives we've talked about. So let's do one more example just to see if we've got it down. All right, so I'll give you an ester. And I want you to try to figure out the name of this ester using what we've learned. So feel free to pause the video, try it on your own first, and then we'll go over it together. All right, so let's figure out what our original carboxylic acid would have been. So again, it's pretty much everything past that oxygen there. And if we kind of go backwards here, our carboxylic acid would have looked like that. So how do we name that carboxylic acid? Well, the first thing we want to do is we want to count how many carbons we have in our parent chain. So we have 4. And remember that this particular carboxylic acid with 4 carbons has a common name, and that name is butyric acid. So again, that's why it's important to know those common names for the carboxylic acids, because we're going to use them to name the derivatives as well. All right, now let's find the group that's bonded to the oxygen, and let's try to name that group that I just circled in green. And again, it's a substituent. Oops, there we go. So let's see, the longest carbon chain, we have 1, 2, 3 carbons, and then a methyl group on top. So we could name this 2-methyl propyl, or there's actually another name we could use for this branched alkane, which is isobutyl, because we have a total of 4 carbons there, including that methyl group. So we could call it butyl, but then use the prefix iso to indicate that it's branched. All right, so combining all of these together, we could actually have 2 names for this molecule, depending on which name we use for the green section. So we could call this 2-methyl propyl butyrate. So we just replaced ic acid with ATE, or if we want to use the other name for our green section there, we could call this isobutyl butyrate. So let's go on to amides, which is our last type of derivative here that we're going to talk about. So this one's a little easier than esters. So let's say, for instance, we're starting with acetic acid again, and we're going to convert this into an amide. And in particular, we're going to convert this into a primary amide, which means that the nitrogen is only bonded to 1 carbon. So to name that amide, we're going to replace ic acid in acetic acid with amide. So super easy. So acetamide. And then let's say we're starting with formic acid. And we form a primary amide. What would the name of that be? So again, we're just replacing ic acid with amide. So formamide. Now, what if we replace the OH group on formic acid with a secondary amine. So we're forming a secondary amide. So let's say instead we have a methyl group replacing one of those hydrogens. Well, the way that we would name this is we would name that substituent that's attached to the nitrogen first. And we want to indicate that it is bonded to nitrogen. It's not bonded to some other part of the molecule. So we would write this as N, so capital N, dash methyl, and then we would finish it with formamide there. I think I'm pronouncing that right. And then what if we had a tertiary amide? So we have two methyl groups there. Well, we want to name both of those methyl groups. And we also want to indicate that they are bonded to the nitrogen. So we're going to be redundant here and write N, comma N, dimethyl formamide. And this is also abbreviated DMF. All right, so kind of similar to when, for instance, you have two methyl groups bonded to the same carbon, you list the location number twice, followed by dimethyl. So here we are doing the same thing, but instead of a number, we're just listing the atom that it's bonded to, which is nitrogen. So we have NN dimethyl. So let's do one more practice problem here. So I'm going to give you another amide to work with. And feel free to pause the video and try this on your own first. And when you're done, we'll go over it together. All right, so let's try to figure out if there are any groups that are bonded to the nitrogen that are not hydrogen. And it does look like we have an ethyl group there. So we would call that N-ethyl. Okay, and then we have to name the rest of that molecule that's on the left-hand side there. So the first thing we'll want to do is count the longest parent chain, or figure out the longest parent chain. So let's start with our carbonyl group, move our way down. The carbonyl group should have highest priority there because it's in our amide group. Okay, and then it looks like we have a methyl group on carbon 5. All right, so I would probably name this here 5-methyl hexanamide. Okay, so let's put all the pieces together. So this would be N-ethyl 5-methyl hexanamide. So that one was a little bit longer than the other examples we looked at, but definitely go through your textbook, work on some practice problems for nomenclature. It can get a little confusing, for instance, with esters, so it's always good to do some practice problems. All right, in our next video, we're going to talk a little bit more about the reactivity of these derivatives, and then we'll look at how to actually make these derivatives. So we'll start looking at some mechanisms and reactions. So I will see you then.